Okay, sorry about the delay, guys, in that. Apparently it doesn't like Adobe PDFs. So I'm Bryony Moody, I'm from the University of Sheffield, and today I'm going to be talking about archaeological sequence diagrams, directed graphs, and Bayesian chronological models. There's a lot of authors on this presentation, so I thought I'd introduce them for two reasons. One is that we're all here, so if you want to discuss anything with us, you can find us. And two is that it's a really interdisciplinary project, and so I thought it'd be nice to show the different disciplines coming into play. So first we have Caitlin Buck from the University of Sheffield, and her main research interests over the years have been Bayesian chronological modelling. We have Tom Dye from Hawaii. He's practiced as an archaeologist for the past 50 years, and he's got a specific interest in practices of archaeological inference. And we have Keith May from Historic England. So that's the UK public heritage body, and he's got a real interest in managing digital heritage data. Finally, there's me. I'm a mathematician by training, and I'm now in the first 6 months of my PhD. And my PhD has been formed to work on a project based on previous research by the other three authors. So what is the project? We're wanting to follow the process from excavating and collecting stratigraphic data through to chronological modelling. So this process starts with the stratigraphic record. So we have both spatial and temporal relationships in this, as you all well know. Then from this, we need to convert this to a temporal sequence. So if we're going to want to model chronologically, we need only the temporal relationships. Once we've got all the temporal relationships, that's not quite the end. So then we want the chronological sequence. The reason why this extra step is needed is because there might be unnecessary temporal information in there that we can get rid of. And then we might want to include any other chronological information that we might have, so historical dating and phasing. And once we've got all of this, we're now in a position to form our Bayesian chronological model. So this is a process that we're really interested in. Actually, I kind of lied a little bit there. The stratigraphic record is separated into two parts. So there's a Harris matrix that you're all probably very familiar with. And we're not saying we're going to get rid of that, we just want to add a step after that as well, called a stratigraphic DAG. And so conventionally, stratigraphic data is held in a Harris matrix, but for chronological modelling, it's really useful to convert this information into a directed acyclic graph. And I will explain what one of them is in a minute, but first I'm just going to kind of go through the process. And so we're interested in this process leading up to it, so kind of the first four boxes. So this is the process. Kind of main steps that we are interested in are the stratigraphic DAG and the sequence DAG. The reason being is that this process is really laborious at present, and we'd like to make this semi-automated if possible. So what exactly is this DAG that I keep talking about? So I'm just going to talk quickly about a little bit of mathematical graph theory, because it might be different to the traditional graphs that you might have in your head. So a graph takes a set of objects and it demonstrates the relationships between them. So I'll give some objects you're all familiar with. So here are two contexts, labelled 300 and 301. And these nodes are used to represent these objects. And then edges are used to represent the relationships between these nodes. Now, if we add a direction to the graph, then the order of the nodes matter. So here I've used the conventional ordering that you use in a Harris matrix, where older deposits are at the bottom and younger at the top. So as you can see, if we swap 301 and 300 round, that clearly changes the information that this graph is portraying. A final thing is that we want it to be an acyclic graph. So acyclic graphs just don't have any cycles in them. And so you can see quite reasonably why you wouldn't want to cycle in this. So if I have another edge linking 301 back to 300, what I'm essentially saying is that 300 is older or younger than itself, which is just nonsensical. So we need to make sure that we have no cycles in. And a DAG is just basically a directed acyclic graph, very inventively named, but yeah, it's a graph that has them two properties. So why can't we just treat a Harris matrix as a DAG? It looks like one, it has nodes, it has edges. Well, suppose we have these four contexts, 1, 2, 3, and 4. And in this dummy example, I'm just supposing that 1 and 3 are above, 1's above 3, 2's above 4, and 2's above 3, and 1's above 4. And then suppose I'm also saying that 1 and 2 were once whole contexts. So why is this not a DAG? We have two issues here. So this equality of the context between 1 and 2 creates a cycle, particularly as well because it's horizontal, you haven't got this ordering. So you're essentially getting this temporal cycle that we don't want. Another issue here is that we have an edge connecting two other edges, and this just breaks graph theoretic conventions. So for the human eye, you might be able to interpret it, but in mathematical graph theory, it just doesn't really mean anything. So to demonstrate what we're going to talk about today, we needed a case study. And so searching for this, as Keith mentioned earlier, it proved quite difficult when I searched for this in the UK stratigraphic archives, UK digital archives. So I was searching at ADS in York, so the Archaeological Data Service. They very kindly gave me access to a lot of their digital archives, and we still really struggled to find the appropriate data that we needed. So I resorted to the library and found some records from Danebury, the Danebury Iron Age hill fort in Hampshire in England. And so Barry Cunliffe and his team archived their stratigraphic information exceptionally well. It was in microfiche form, so I had to go and find a machine to read it. But once I'd done that, I had these quite kind of deep stratigraphic sequences, which is what we needed. So I'm only going to focus on a really small part of one matrix from a very, very large site. The reason being is just for visual reasons on a presentation. And the section that I'm looking at was dug from 1977 to 1978. So just a quick kind of what have we done so far, because we're quite early in the project. As Keith mentioned, I and Book have published a paper outlining the theory behind using DAGs to represent chronological and stratigraphic information. And they used Çatalhöyük as an example in their paper. Due to the deep stratigraphy, it made an interesting case study. In addition to this, open source prototype software called HM is available in Lisp with very good documentation besides it for helping you to kind of learn as I've been learning to use it. So I would recommend looking at that if you are interested. So getting on to the case study now, here is the Danebury Harris matrix that I'm looking at. As I mentioned before, it is part of a Harris matrix. It's not the full one that was found in the archives. Now, I know that colouring phases isn't convention in Harris matrix. There's no need for that because you structure the phases physically. But for consistency with the other graphs that we're going to look at, I've just coloured them. So we've got orange is phase 3, blue is phase 2, and pink is phase 1. So now this is what I call a stratigraphic DAG. So this is purely the physical relationships between the contexts. But we have a few issues here. So you notice here we've got the floating node 5113. And the reason for this is that in the Harris matrix, it had no physical relationships with any of the other contexts. Other than that, it was a once whole context with 5512, which is now 551, sorry, which is now down here. But it actually had no physical relationships with any of the other contexts. And as adding a once whole relationship created a cycle, we've excluded that. As well as this, it's removed some edges. So you can see here that 465 and 464 only have edges going to 476. This is because if we look in the matrix, we've got 465 and 464, and it has an edge going down to 564, but it also has an edge going over to 476. And because 476 is itself above 564, the Harris matrix, the HM software decides that it doesn't need this edge. So the edge in red, it says this isn't useful for me. I'm only wanting the chronological information. And so it's edges like that are deleted at this step in the process. So now we go on to a sequence DAG. So those qualities in the previous slides, such as 465 and 464 being once whole, these are clearly useful, both temporally and stratigraphically. So we include them here. But this changes the structure of the DAG. So this is clearly implying physical relationships that aren't true. So here you've got 513 and 551 are above 562. So we know from what I said before that 513 wasn't actually above anything stratigraphically. We just know that it was once whole with 551. And it's because of this reason that we can't go back in the process. So here we know that either 513 or 551 or both are above 562, but we don't know which one. So this is a one-way process, just a note to make. So this is now what I'm going to call a sequence DAG, and I'll refer to this as sequence DAG 1 because there's more than one that we're going to look at. So the relationships here that are represented are now purely temporal. We're not representing physical relationships here. And the reason for this is that we're wanting to get to chronological modelling, so that's not an issue. Now, the placements of the nodes, I admit, isn't the most intuitive with the phasing. This is why we've included the colouring. The placement of the nodes is determined by off-the-shelf visualization software that is used for mathematical DAGs, and as a consequence of that, they want as little edges crossing over as possible, hence the placement of the nodes. So going back to the matrix again, we've got some other relationships here. So we've got these contemporary relationships, and obviously they're also useful when doing chronological modelling. So this leads to sequence DAG too. So here we've included both the once whole context relationships and the contemporary relationships. And so this again changes the structure of the DAG. But these two sequence DAGs are not the only possible ones. So there are actually 5 extra equalities that are included in the contemporary relationship, from the contemporary relationships. So what if you're less certain about some contemporary relationship than others? Well, if you want to look at the different combinations that you can have of sequence DAGs by including or not including these 5 different contemporary relationships, this produces 32 different sequence DAGs. Now, that would be quite tedious to present them all to you, so don't worry, we're just going to proceed with the 2 we've looked at, which are this one on the left, which is using all of the contemporary and once whole relationships. So that's stratigraphic DAG 2, and then stratigraphic DAG 1 just includes the once whole relationships. So this leads us on to our next stage in the process. It's a chronological DAG. So in a chronological model, the nodes now represent known or unknown calendar dates that we want to estimate. So an example of this is the start of a phase alpha, the end of a phase beta, and a date of an object or a context theta. So these Greek letters haven't just appeared out of nowhere. They are convention in all the publications about Bayesian chronological modelling, so I've used them for consistency, basically. And just to note that the chronological DAG does not map one-to-one with the sequence DAG, so we're including information and taking it away, as mentioned earlier. So going back to the Harris matrix, suppose we found datable finds in the coloured context, so 7 in total. So we can produce this chronological DAG here, where we have the start of phases, such as alpha m, so start of phase 3 is at the bottom here, the end of phases, so beta m is the end of phase m, and then anything that's dated theta n is the date of a context found in context n. So here's another one. What if we want to date the context that we don't have dating evidence for? So we can do this. So if you include them in the chronological model, then we can model these relationships. However, this should be treated with caution because we have got more parameters that we're trying to estimate, in this case, the dates of both the rectangle nodes and the oval nodes. We have more parameters to estimate than we have data. And so the data comes from the nodes that have oval shape. So it's something that's possible, and it's something we want to explore, but we are aware of its limitations. A final idea we might want to look at is about residuality. So say that we found data and evidence in context 489, but we're not convinced that it wasn't from an earlier context and then redeposited. So then this changes the structure again, and now theta 489 down here no longer has a relationship with context 488 or alpha 3, because we can't even be sure that it comes from phase 3 anymore. It might have been from an earlier phase and redeposited. So even for just one sequence DAG, so all of these chronological DAGs were formed from sequence DAG 1. And from that, we've had 3 chronological DAGs already that we've looked at from these hypothetical situations. So it's a problem that grows quite quickly. So I mentioned at the start of the talk that this is the process that we kind of go through, but I basically fibbed a little. And it's actually something that's a little bit more like this. So we start off with the Harris matrix, we then proceed to the stratigraphic DAG, but then we have multiple sequence DAGs that we can consider, and from each sequence DAG, we have multiple chronological DAGs that we can consider. So this sequence DAG number n here, there's n number of sequence DAGs. In our case, I said there was 32. How big does this problem scale up? So what does n equal? Well, given k possible equalities, so k possible equal relationships in time that you may want to consider for your chronological model, that gives you 2 to the k possible sequence DAGs. So how big does that grow? So when does it become, say, for example, 1,000,000? That's a big number. So just 20 possible relationships to consider gives you over 1,000,000 possible sequence DAGs. So you can see that it grows quite quickly. So what are the aims for the rest of the project? As I said, I've just started my PhD. We're quite early in. We want to make the graph drawing software as intuitive as possible. We appreciate that, for example, the placement of the nodes with the phasing isn't particularly intuitive. So we want to look into considering how we'll manage that. We want to write an interactive interface to allow archaeologists to combine chronologically equal nodes and delete chronologically unnecessary edges. And then we also want to allow them to be able to identify key nodes with date and evidence and those without, but that they want to estimate dates for. And then we'll also need software to render the chronological DAGs ready for input into existing Bayesian calibration software, such as BCal and OxCal. So at practice, present standard practice involves taking one chronological sequence and deciding that that's your main one. But as I mentioned before, there's possibility of considering multiple different sequence DAGs, chronological DAGs, and so on. So how are we going to manage that? So we're aware that we're going to need to. So we're going to want a method for automatically converting chronological DAGs into priors, ready for input into Bayesian chronological modelling. We'll also want automatic tools to allow the archaeologist to identify the most plausible graphs and proceed with them. So that might be that'll probably be statistical tools, but that's something we need to consider. And then we also need a development for the standard of archiving competing stratigraphic sequence and chronological DAGs, because there just isn't one at present. So thank you very much for listening. Just some quick references. So this is the number 1 paper that's been established for the theory behind what we've been talking about. Number 2 is the link to the GitHub page with the software and all the corresponding kind of tutorials you need for it. And then also, if you're interested in Bayesian chronological modelling, then chapter 9 in this book is a really good way to kind of get into it. And yeah, so thank you very much for listening.